Okay, so thanks a lot for having us here speak. My name is Eli Ben-Sasson. I'm the chief scientist of Starkware. I'm also joined here by our head of product, Avihu Levy, and by our board member, Harish Devarajan, who's sitting there. Please come up and talk to us afterwards. Any one of us will be happy to talk to you. We'll also be at DevCon 4 next week, a bunch of us. And today I want to tell you about the current state of the Stark as we're developing it at Starkware. So roughly we'll go through over what is a Stark. We'll compare this particular technology to Snarks, to recursive Snarks, to Bulletproofs, with an emphasis on scalability, which is the main strength and the main plan of deployment for Starks. So we'll focus on the benefits of Starks for scalability. Time permitting, we'll look at potential use cases. And there's also, for those who will stay long enough, there's hopefully something of a surprise that I hope you'll enjoy. So let's dive in. In general, this is going to be talk about a technology for proving computational integrity. And if you look at the word integrity, it means the quality of being honest. So computational integrity means the quality of a computation being executed honestly or correctly, meaning that the outputs reported are indeed in line with what the program specifies and the inputs imply. So if you try to find an analog for what a proof is, then I think a very good one for non-developers and people who are not proficient in math and computer science would just be something like a grocery receipt or a restaurant bill, because it is a string of characters that is used to enforce and facilitate and establish integrity, that the sum being paid or requested to pay is indeed correct with respect to the inputs. And the way this proof works is that if you want to verify or produce it, the way you verify it is pretty much the same way it is produced. You would look at the inputs and you would sum them up. And this is, so the production of the proof is the same as the verification process. We'll call this naive verification. It's naive because it's the simple way to verify that a computation is correct. You simply re-execute it. It has some very good aspects. This proof is completely deterministic. It's either right or wrong. There's no chance of error. And you just get this string. You can just read through it. Now, the kind of proofs we'll be talking about, and all the kind of more exotic proofs that you read about, things like Snarks or Bulletproofs, and there are a bunch of others that I'll mention later on, they're a little bit different. First of all, they involve some kind of randomness, often also a little bit of cryptography. They do always permit some small chance of error that hopefully you want to quantify and make very small. And also, at least at the start, they have some version of interaction where there's a back and forth going on between, in this case, it would be the owner of the grocery and the person buying. But in return for these things, for these caveats, you get many, many benefits. So let's just go over them. First of all, this is a very vibrant and thriving field of research within cryptography and theoretical computer science. That's how I personally got involved in this thing. My background in my previous vocation was a professor of computer science at Technion, Israel's Institute of Technology. So these marvelous constructions were invented in 1985 by Goldwasser, Mikali, and Rakov. Famously, Goldwasser and Mikali got the Turing Award, the highest award in computer science, in large extent for their work on these kinds of proofs. Again, there are more than 30 years of fantastic research into these constructions. Okay, so what are the benefits? First of all, you get zero knowledge. So an analog, or a way to think of it, is that you can blind out whatever parts of the input that you would like to, and then when you see this kind of receipt or proof, you know nothing about those inputs that were blinded out. And you get to choose which inputs you're going to blind out. And then another thing is scalability. So this took a while to figure out and get to this state, but here's what you can do. If the computation lasts t cycles, and you think of t as going to infinity, then the time it is required to generate a proof scales almost like t. Roughly, it's called quasi-linear in t. It's t times polylogarithmic in t. Think of it as something very close to t. And here's the marvelous thing. The time needed to verify the proof is exponentially faster than the time needed to execute the naive computation. It works like logarithm of t, or exponentially smaller. For instance, log of 1,000,000 is 20, log of 1,000,000,000 is 30, so it's a very small number compared to t. And this aspect of scalability is what we are going to use later on for helping scalability in blockchains. Another aspect that is worth mentioning is universality. So you can apply this to any computation that you can specify by a program and which runs for t cycles, for any parameter t. These things apply, the zero knowledge aspect and the scalability. So here are some examples that you can come up with things that could be useful if you could prove. I paid all my taxes on all my cryptocurrency transactions for the year 2017, and I'm not revealing any information about the inputs that went into it. I could prove that I control at least a collateral of 10 bitcoins as of today. If I'm an exchange, a crypto exchange, I can prove to each customer that I'm in the black as of today. This is something that we wrote a blog post about, and it's posted in the Coin Center's webpage. You can read more about this last thing. So now I want to talk about Starks, because they are a recent arrival to the scene of zero-knowledge technology and of proof technology. So I want to talk about what constitutes a Stark. So you probably heard that there are many, many theoretical approaches and techniques to getting proof systems of various sorts, zero-knowledge proof systems and other kinds of proof systems. Here's a very short list that some of the famous names. There are many others that I didn't mention here. And there are also many, many implementations, a lot of them open source, that you can use and play with. Here I'm mentioning a few more. There's a pretty comprehensive list at zkp.science that I urge you to look at, the list of all the open sourced code bases for generating all kinds of proofs and a lot of pointers to the literature. Okay? So when I talk about a Stark, or a zero-knowledge Stark, so you can have a Stark with zero knowledge or without. So it has to satisfy a few requirements. It has to be a proof system, first of all. If it's a ZK Stark, then it has zero knowledge, meaning that you can shield or blind whatever inputs that you choose. This technology has to support that. It has to be scalable, as we previously spoke, meaning that generating a proof takes roughly t cycles for a t cycle computation, and verifying the proof is exponentially faster with no extra assumptions, okay? No setups, no parameters generated, no pre-processing. Just when you see the computation for the very first time, this is what needs to be done in order to verify it. And this is an aspect that makes scalability in Starks very unique, but also very powerful for blockchain applications. The other thing, that's the letter T, it has to be transparent, which means that the verifier's messages are only public random coins. Okay, so it is, you can think of it as an interactive system where there are messages going between the verifier and the prover. You can also replace the verifier messages with some random function or cryptographic function, and then you'd make it less interactive to the point of being even non-interactive at all. But the main thing is that the messages that come from the verifier have to be random coins and nothing else. And this includes setup costs and everything like that. And the last aspect is that you can actually prove that whenever you see a proof, the party doing this proof actually knows a witness or knows those private inputs that would be required to generate the proof. And the way you do it is by extracting, there's formally an efficient procedure that can extract the secrets from the prover. So that's the ARC part. I want to say that Starks may be interactive. You can make them non-interactive by always replacing the random messages from the verifier by some, by some cryptographic functions. And you may even want to use them interactively in the context of a blockchain, because you could use the randomness coming from a blockchain header to simulate the randomness of the verifier. And if you do that, you could work with much shorter proofs and that are also much safer than having a non-interactive version. And there are code bases for a Stark without zero knowledge. It's called SciPOC. We presented it at Eurocrypt 2016. And there's also even a zero-knowledge Stark academic code, which is libstark. Both of them are available on GitHub. So now I want to compare Stark to Snark and to Bulletproofs. Not because, I mean, there are other zero-knowledge technologies and other proof technologies out there. And, as time passes, there'll be more and more, which is, of course, a great thing. But these are two very famous ones and often cited, and they're actually already in use in blockchains, right? So that's why I'm focusing on them. So, and I want to focus on scalability because the main new and important aspect in a Stark is its scalability property. So I want to compare Starks to Snarks and to Bulletproofs, and even to recursive Snarks in this aspect. So our starting point is naive verification. If someone has performed a computation that takes t steps, so think of this axis as showing t, how many steps it would take to just run the computation. And if you want to naively verify it, as you would do with a grocery receipt, then your proof activity time, the verification time, would be exactly the same, right? You would just rerun the computation. So t steps to prove, t steps to verify. Okay, no zero knowledge, no scalability. Now, the definition of a Stark means that you get this different behavior. The prover activity scales almost linearly as the naive one, but it is a little bit higher. We would love for it to be exactly equal to naive, but we currently don't know. And it's a big theoretical open problem whether one can even make it linearly related, proving time to naive execution time. So the best we can currently hope for is that the prover will be quasi-linear or very close to linear. But the main thing is what's happening here with the verifier. The verifier's running time will be going up very, very slowly, logarithmically slowly, which means that for large enough computation, you will get this effect where verification is much faster than naive computation. And that's how you can deploy this, let's say, on a blockchain. Think of the naive computation as being processing, a block of transactions or 1,000 blocks of transactions. So now instead of all the miners in the world doing the same computation, you could have a prover running for a little bit longer, but then everyone else just becomes a verifier, okay? So a system that has this property with transparent, no setup costs and only public randomness used by the verifier is a Stark. Let's see how this compares to Snark, which is famously used by Zcash. I should also mention I'm one of the founding scientists of Zcash. I strongly support Zcash, and I think Snarks are great and Zcash is great. But for scalability, for privacy, the zero-knowledge aspect is really useful, and that's how it's used. But for scalability, Starks are a little bit better, and this is why. So in a Snark, the verifier time is indeed logarithmic, but only if a trusted setup phase was performed, and it must be performed by someone trusting the verifier. And as the computation grows larger and larger, you would need a larger and larger setup time, and it has to be trusted, and larger keys. Okay, and the prover time is also a little bit more time-consuming than the Stark ones for cryptographic reasons of what kind of primitives are used there. So just to summarize, you in a Snark require a trusted setup, and it scales linearly. This trusted setup phase scales linearly with a compute time, which is why this is not a Snark is not a Stark. Now, there's also this notion of a recursive Snark, in which you still have a trusted setup, but you could make the trusted setup very, very small so that the trusted setup phase doesn't scale linearly with the computation size. Basically, you break the computation into a sequence of epochs, and each epoch is very small, and you only need to generate keys for one epoch. And then that's how the system works. So this seems very good for scalability, but a point that one should be aware of is that the proving time, while it also scales quasi-linearly, the constants there are much worse than for at least our transparent-based technologies. And you still require a trusted setup, but you have much larger proving time. Now, you might say that this doesn't matter asymptotically, but it might matter if you want to use something like a recursive Snark for scalability. So let's suppose you're willing to accept only one block delay. Okay, so the time you would need, the blow up in generating a recursive Snark proof might be just too large for you to get any scalability benefit, right? Because the further down this axis you go, the larger the benefit for the verifier over naive computation. But if you have such a blow up in proving time, you might not reap a lot of benefit from verification, from the scalability. And with a Stark, you will be, because the Stark prover is more efficient, you will be benefiting more. You'll get a bigger discrepancy or a factor of savings of verification over naive computation. So finally, I want to talk about Bulletproofs, which was just implemented in Monero. So, even though I'm affiliated with Zcash, I think Monero is a really great project, and I support it. I think, we should have a lot of different technologies deployed. And so Monero just introduced Bulletproofs to enhance the privacy of transactions there, the zero-knowledge aspect of Bulletproofs. And so with Bulletproofs, what happens is that the proof length, the communication complexity, scales very well. But verification time actually grows superlinearly with the computation time. So as a zero-knowledge technology, Bulletproofs might be very good, but it is also, by the way, it's a transparent technology. You don't need any trusted setup, which is really great. But as a scalability solution, the verifying time scales linearly with the naive computation time. So this really doesn't give you any savings if you want to apply it to scalability and to let verifiers work less. It could help you if you only care about scalability in the form of how much information you're keeping on the blockchain. But every miner processing that information will have to run in time that is linear and even superlinear in the number of transactions. So I just want to show you some actually measured times for verification, both as I extracted them from the Bulletproofs academic paper, and there's a much better open source library called Dalek Cryptography. And then what I did is for this graph, I just actually executed on my computer, and I also executed the Stark verifier on my computer, and here are some numbers. So for the numbers that the tests report in the Bulletproofs paper and in Dalek Cryptography, you can see, and this is naive computation time for basically Peterson hashes, which is what many of the proof systems out there are using. So the sapling circuit of Zcash is going to use Peterson hashes. The Bulletproofs implementation uses Peterson hashes. And that's also something we implemented at Starkware. So you can see the effect of scalability of the Stark verifier as compared to the running time of the verifier that grows with the running time of the naive computation in a similar kind of fashion. Okay. So I want to zoom in now and show you some numbers. Again, all of these numbers were generated on my laptop, which is a T440 Lenovo at 1.8 gigahertz on a single thread. So if you look at that region, and here we're measuring running time in milliseconds. So if you look at that region, this is roughly what we estimate to be the naive computation time for doing repeated invocations of a Peterson hash. So it's roughly 5 hashes per millisecond on a single thread. And what we have here is, here we have a logarithmic scale, a doubly logarithmic scale, and we see that the naive computation time for generating and verified Peterson hashes looks like a line. Here is the measured time for the Stark verifier. It goes from roughly 10 milliseconds up to 23 milliseconds for 8,000 hashes. And the proving time is roughly a factor 100 more. So it takes roughly 100x time to prove that you executed a number of hashes than it actually does to compute these hashes. Okay? And I just want to say, all of the numbers that I'm presenting here are work in progress. We haven't finalized anything. In particular, it's single thread. There are a lot of optimizations that we haven't used yet. So I think this 100x is going to go down, I guess, could go down by an order of magnitude or a little bit more. Both in the prover and also in the verifier. Okay. So I also just want to mention a little bit some points about why transparency is important, why the fact that Starks have no trusted setup is really useful in settings of blockchains. So first of all, you're eliminating a very significant single point of failure, which is the trusted setup. Think about a system in which you are going to put a lot of value, something like Bitcoin style, could be hundreds of billions of dollars worth of value. That would be a very major incentive for large, parties or even governments to try and, compromise that. So by eliminating this single point of failure, you're enhancing the safety and security of your system. Another point is that this also allows continuous deployment of minor upgrades to your system because you don't need to regenerate this very elaborate trusted setup ceremony every time you're doing some improvement to your code. And that's very important. It's also important in an open source community of developers where different parties can be developing different applications using Starks, and you don't need to ask yourself whether you trust the setup ceremony for these other parties when they're using it. So you're reducing trust assumptions. And as a side benefit, because Starks, they actually rely on very little cryptography and very old cryptographic tools, they are somewhat faster and safer. So they're post-quantum secure. You have faster proving and verification time. You have simpler and more reliable trust assumptions that go back to 3 decades of research, and these are things that are more easy to trust as far as cryptography goes, as compared to some more recent assumptions that you would like a few decades to pass before you can really trust them. That's at least what scientists would say. So I just want to summarize again the virtues of Starks for things like scalability. And I have here a Stark, a Snark, and Bulletproof. Again, there are many other implementations and approaches out there, and there will be more. So I'm just talking about these because they're rather popular, and they are actually deployed in blockchains. So Bulletproofs and Starks don't have any trust assumptions, meaning they don't require trusted setup. They are transparent, which is good. If you look at the crypto assumptions, again, Stark and Bulletproofs have somewhat of, again, better reliance on them. And quantum safety, both Snarks and Bulletproofs rely on number theoretic assumptions that are breakable by efficient quantum computers. And here are some numbers, the latest ones. So this is a slide that we also presented 1 year ago at Consensus 2017. And there we reported that the proof length of a Stark from the academic paper has gone down from 500 kilobytes to 80 kilobytes, but we actually brought it down to 45 kilobytes, and we have yet to identify a lower bound. It might go down a little bit more. That's for a single transaction. But we talked about how scalability works very well in a Stark. If you were to batch and create a proof for 10,000 transactions, which is completely doable, on a standard computer, and that's where we're heading, it would only be 135 kilobytes or 3x greater than this, even though you increase the payload size by a factor of 10,000. Snarks and Bulletproofs have much shorter proofs, but again, Bulletproof's verification time would scale linearly with these 10,000 transactions. And with a Snark, you would require a very large key that everyone who wants to prove would need to download, and which requires a trusted setup for that. So now I want to go a little bit deeper and tell you about how we go about building Starks at Starkware. So what we do is we take your computation and we convert it to something that is called an algebraic intermediate representation, or AIR for short. Now, what is an AIR? Those of you who have looked at things like libsnark and the Zcash construction and know about R1CS, I will say this. R1CS is a special case of an AIR. So every R1CS is in particular an instance of an AIR, but an AIR can be more general. You can work with constraints of larger degree than 2. That's perfectly fine with a Stark. You don't have to have this separation into 2 linear forms that you take a product of. So it's slightly more general, which is easier to use by developers. We take our computation and we convert it into one of these AIRs, and then the state of the computation is captured by a bunch of registers, where each register is a field element coming from some finite field. It could be a prime field, it could be a binary field, it could be actually any finite field of your choice. And then we represent the program as a set of constraints on pairs of consecutive states. So if you go from state A to state B, whether this is a legal transition for the particular program you're working with, this will be defined by a set of constraints. And each constraint is a low-degree polynomial. We'll give some examples, very simple examples soon. And then we apply a lot more algebra and cryptography that I won't go into right here. So I guess the takeaway message from this is that if you're familiar with the R1CS constraints from Snarks, they are a special case of the kind of constraints that we write with Starks. So long term, we'll probably have a tool chain where you won't, as a developer, have to worry about this at all, and you will just write your program in whatever it is, Solidity, Parity, C or Python, and it will be converted into AIRs, but that's very long term. Midterm, we'll probably have some domain-specific languages for cryptographic uses and very particular things that will be more efficient. But in the short term, we're just hand optimizing AIRs. Our team is working on doing the most optimal ones for very specific computations like the ones that I'll describe next. So here's our first milestone, internal milestone, that is also related to things that we committed to the Ethereum Foundation. I want to prove that I know a leaf in a Merkle tree of depth D that has a Merkle root R, where everyone knows the Merkle root. So think of this Merkle root R as the state, the public state that everyone knows, and I want to show that I know, some leaf in it. And this is very useful. This is the bulk of the sprout circuit and the sapling circuit in Zcash is actually comprised of doing things exactly like this. So in sprout it was SHA-256 was the hash. Now sapling is moving to Peterson commitments and Peterson hashes, which is what we also implemented. It's also useful for verifiable delay functions where you want your verifiable delay function could be I invoked this repeated hash many, many times, and the output from a known X is this Y. So that's another application you could use it for, and it's also it could be used in scalability solutions in various places. So this was the first internal major milestone that we took on ourselves. So we incorporated less than a year ago, but we have a very, very strong team of engineers and mathematicians. So I want to show you some numbers that we currently have. So again, this was on my laptop. This is Avihu's laptop. It's probably faster, so you would get better times. But my laptop is a Lenovo ThinkPad, 1.8 gigahertz. This is the running times just from a few days ago. Again, this is all work in progress. The numbers are constantly coming down. Proving time for a path length of up to 250 takes less than 7 seconds in single thread. I just want to point out that at this range is what you need in order to do something like a Zcash sapling transactions. This is roughly what you need. So right now, at single thread, my laptop, this would be 3 seconds. Verification time, you see, is hovering between 10 and 20 milliseconds. And again, this will go down. All of these numbers are expected to go down. And this, again, all of this measured on my laptop. This is the prover time and the verifier time for going up to 8,000 invocations of repeated hash. So at the end, it takes, less than 5 minutes, I think. 4 minutes, roughly. And verifying it takes 23 milliseconds, okay, for a path of length 8,000. And then in terms of the proof length, so this is how it scales as you grow up with the numbers. So it's on a logarithmic scale here. So for one transaction, you're looking, depending on the number of bits of security, you're looking at between 10 and 20 kilobytes. But when you go up to, so this is 1,000, 10,000, 100,000, million, 10 million, 100 million. Okay, when you go up to, I think this is 10 billion transactions. Sorry, 10. If you were to prove a Merkle path with 10 billion transactions, 10 billion invocations of hash, this would be either 120 or 256 kilobytes long proof, okay? For the proof that says I ran this, let's say it's a VDF or something like that. And verifying it, again, would take a small number of milliseconds, okay? Now, if you ask, okay, if I'm a verifier on some blockchain, what is the work that I need to do? So most of the work you need to do is verify authentication paths. That's basically what goes on in a Stark. There is a commitment to some function, and then there are openings of various values. And most of the work of verifying a Stark proof is verifying Merkle authentication paths. And this is roughly the number of paths you would need to verify. So again, for some transaction that covers 10 billion hashes, you would spend, depending on the bits of security, you would spend between 4,000 and 6,000 hashes. You would, as a verifier, instead of spending naively 10 billion hashes, you would do either 4,000 or 6,000 hashes to verify it. So you're saving to a very large extent. And for those familiar, when we'll get to implementing recursive Starks, this is what you can use to save, right? Because Stark verifier of a Stark prover that says I ran a verifier really will be saying I did all of these Merkle path authentications, so a small number. Now I just want to mention also a little bit about, so early on we said that Starkware, so Starkware is a company, it's a for-profit company. Famously, we're not doing an ICO, we don't have a coin. We would nevertheless like to raise revenue and make profits. And one of the early things we explored, and we're still open to it for the right partners, is the tech for token model, which says that we invest not money but technology in various blockchain projects or coins that we like in return for some revenue in the form of coins. So the first such project is this Ethereum Foundation grant, in which we received upwards of $6 million worth from the Ethereum Foundation in order to develop Stark-friendly hash functions and implement them. So we defined the complexity parameters of Stark-friendly primitives. We'll present a lot more on this at the DevCon 4. This is like a preview. We teamed with a respected team led by Professor Reimann. He's the Ryan Reindel cipher family, which is behind AES, Dr. Tomer Ashur and Simon Tuge. And they already submitted their first report that they will publish shortly. It's a Reindel AES-based construction of a Stark-friendly hash. It's called Jarvis because Jarvis is a famous character from the Tony Stark's Iron Man comic strip. We weren't aware of this, but Seaman, found this marvelous name. And Friday is another character there. So Friday is the Stark-friendly hash candidate. And the bottom line is that it's 25x faster to generate for it a proof than it is for Peterson. So it means that whatever the numbers are for generating proofs for Peterson, you can get 25 more hashes or encryptions if you were to work with Friday. So a lot more is going to be revealed soon about this, and we would like to involve the public in reviewing this and seeing if it is actually safe to use and secure. Another thing is that we committed, that's part of our agreement with the Ethereum Foundation, we committed for a two-year project in which main deliverable, or one of the main deliverables, is a Stark proof at a rate of 100 hashes per second on a quad-core computer. As I just showed you previously, we're roughly running at 100 Peterson hashes at for 3 seconds. So, and that's on a single thread. So if you just move to quad-core, even without going to something more efficient like Jarvis and Friday, we're probably already pretty close to the milestone that we promised them for a 2-year. So this is less than half a year after we signed this, got this grant with them. And again, if we use something like Jarvis or some other construction, probably will hit even faster running times. And this is, again, thanks to this very marvelous team of engineers and scientists that we've accumulated. We're also hiring. The one thing you should know is we're located in Israel, but if you're willing to commute there or interested in a job and you're a really good programmer, C, C++, and math, then please talk to us. So again, these are just the estimates for how things would look with Jarvis in terms of proof size. It would go down for 10 billion hashes. It would just be around 100 kilobytes. And now I want to invite Avihu to show a demo of, why don't you explain what you're going to show?
Hi, everybody. Sorry, that's my voice, stronger a little bit. So my name is Avihu. I'm head of product in Starkware. And what I want to show today, I think it's the first time ever, as far as we know, that we are showing, that somebody shows a full proof system in a browser. So I'll go over some simple examples first, just to let you understand what's happening on the screen. So the first very simple example is the one of Fibonacci prover. So everybody are familiar with Fibonacci, right? So the claim that the prover here wants to prove is a very simple one. The secret in the claim is what is the second number. And the claim is I know a second number, such as a Fibonacci series starts with a 1, and the second number is secret that only I know. So a Fibonacci series in the length of 1,000 end with a specific number. This is the claim, okay? So the secret here again is the second number in the series, and once I will click generate proof, what's going to happen is that the prover will first compute what should be the last number in this 1,000 number series of Fibonacci. And once he has this number, you have the full NP statement, and then he's going to prove it. And so you will see a proof being generated here on the browser and being presented. Let me just generate a proof. Okay, this was pretty quick. So here you can see that now we have the full NP statement with our secret that the second number is 1. And we got a proof that we can now take we still also need the last number because it's part of the statement. Yeah, luckily this works and proof is correct and everything verified. And it's very important to realize that the verifier expects a specific statement. So if you change the statement just by a little bit, for example, you take a sequence to be not 1,000 but 999, then the proof will fail, okay? So this is a very simple toy example to just show how this interface operates. Let's move to a little bit more practical example. So a hash prover, meaning I know a preimage of a given hash, okay? So again, what's going to happen is that I'm going to run the prover. He's going to first generate the hash output. Depends on the secret preimage I have. Here it's 1. And then the NP statement will be, I know the preimage of some given hash output. Okay, so again we can take the proof. We also need to take the output of the hash function. And then the verifier can verify that we actually know a preimage for this hash value without presenting what's the preimage is, of course. And the system is, of course, sensitive not just to change in the NP statement, but if you change even one bit of the proof, then you can see that that the proof will again be invalid to the verifier. Okay, let's go to something even more useful. So Eli presented before the idea of proving that you know a Merkle path. So this is actually being used in many different scalability and privacy application. Sometimes you want to prove that you know some leaf in the tree, for example in Zcash. Sometimes you want to prove that you change accounts correctly. For example, when your Merkle tree represents a state of all the account balances. And sometimes you want to prove that trades happened correctly. So in all these, in all those statements, basically what you want to prove is that you know some Merkle path where the Merkle root is given, and the Merkle leaf or the leaf in this path is or not. In this case, we are using a leaf which is known. So the secret here is the path from a leaf to a root. And when I will generate the proof, this one is much heavier computation, so the proof will take some time. So when I'm generating the prover is going to complete for me what's the correct root given some secret hash. And after some time, I guess, yeah. So we will get a proof that we know a Merkle path from this leaf to the root given here in the statement. And again, you can just make sure that verify even a longer or a harder statement works. Yep. Yeah. So this is it. It's I think a very strong possibility to have, and I wanted to try and show one more thing. Just 1 second.
I just want to mention that what's going on here is the browser is executing WebAssembly. So it's running in the browser on WebAssembly, which again our engineers compiled to. And again, this is now probably going to be the very first time that a public display of a foolproof system running in a browser on a smartphone.
Well, I don't promise that it will work on the first try. Okay. Sorry. Yeah. So yeah, this is. Let's just. It's the same NP statement that you've seen before on the computer, but now it's running on my phone. So yeah. Let me refresh here. Yeah, I know, but it's.
No, but the password, wait.
Yeah, but the password is, they will not say it.
Just 1 second. They won't see it? Okay. Yeah, questions meanwhile. Yes? No, not that sometimes it. In all proof systems, there is a probability of error, which means, or stated differently, in all proof systems, in all interactive-based proof systems, so this includes Snarks and Bulletproofs and all other proof systems where you have a proof that is shorter, It means that if you have unlimited computational power, let's say you can run a computer for 2 to the 128 steps, you will find a proof of a false statement. It holds for all of them, okay? Or if you get lucky and fall on, something that happens with probability 2 to the minus 128 or 2 to the minus 80, depending on your security parameter. This is, it is provably necessary. You cannot have succinct proofs for general languages or for general computations in which you do not have a probability of error. This cannot happen. It will contradict Turing's halting, undecidability of the halting problem and other things. So it's not like there's something, we would love to have succinct proof systems with 0 error. It is mathematically impossible to have them. So all these proof systems have a probability of error. It's a parameter. In all these systems, you design various properties of it in order to achieve your target security. So for instance, here, we actually have, in this particular implementation, you choose between 80 and 128 bits. It's a parameter that you choose for. Of course, the more security that you want, the higher the complexity of proving and verifying and proof length is. Again, this is a property that is common to all proof systems, in particular, Snarks, Bulletproofs, Starks, and all the others. More security implies more resources.
Okay, let's try again.
Yeah, so you see it's 80 bits of security right now.
Yeah, and it's running at least. Maybe it will even.
So again, this is the first demonstration of a proof system being run on a smartphone inside a browser. So it's a browser running WebAssembly to generate a proof.
Yeah, it took just a little bit under 16 seconds to run a prover. Yeah, I guess I'll say a few more words about it, more than you mentioned. So, so basically, just I think that it's the first time that you can see full proof system cross-platform on browser, and as Eli mentioned before, I'm sure the numbers will get even better, and I guess that we will take questions now.
Yes, we'll take questions, and then we also, time permitting, so Avihu will also discuss our. As we said, Starkware is a company that we're not building our own coin. We want to. We're currently in the very last stages of exploring what our first line of products is going to be, and time permitting, after the questions, we'd be happy to go through that. Avihu will go through that. So, yeah, question. Yes. Let's check it out.
I can meanwhile.
Oops.
No, it's okay. I already set my password to be something stupid. Yeah. So I will just mention.
So that was, I think, 16 seconds. Let's see how much.
Yeah. The point is that proof time wouldn't change by much because.
I know, but let's.
It was 16 seconds.
But let's say that after we see that it's not much more than 16 seconds.
Hopefully.
Come on.
Okay.
Okay, so I'll explain. What is happening is in a Stark proof, the prover is committing to a bunch of functions that are, sort of an encoding of the execution trace of the computation, okay? And then, after committing and sending Merkle roots to the commitments, the verifier asks a number of questions, and the prover opens them up, those queries. Now, the number of openings up is what is defined by the security parameter. In particular, 120 bits means that the verifier is asking, 33% more, whatever is from, yeah. Sorry, 50% more, sorry, 50% more queries, and the proof length is going to be roughly 50% longer for the 120-bit. But the prover, most of the work of the prover is in generating the Merkle commitments for the various functions. And then opening them up is negligible. So here it was like roughly in this sample size of 1, it was like maybe 10 milliseconds for maybe accounting for the extra work of opening up 50% more paths. Maybe yeah. Great question. So, okay, you can generate, okay, Starks, and this is another difference between Starks and proof systems based on number theoretic assumptions. So Bulletproofs and Snarks are based on number theoretic assumptions, which means that you have to basically work in a somewhat specific kind of prime world. It's a safe prime, and it must have some pairings and elliptic curves with it. With Starks, you can work over any algebraic domain. So you can work over binary fields. You can work over very small prime fields. The prime field could have 30 bits. It's fine. It could be a binary field of that size. So now the question is, which field do we work with? So okay, the academic code, which is open on libstark, worked only in a binary field, in GF2 to the 64-bit field. Okay, only there. What we first implemented was only for prime fields, and because Peterson hashes, which everyone else is using, is in a prime field. But again, our Starks can work with any prime field, so that's what we implemented first. We're also going to be implementing, or at least exploring, binary fields. Which ones do you want to pick in which setting? That's a very complicated question that depends on many factors. I'll give a few examples. If you're going to be implementing, if most of your computation, for instance, is going to be something that is AES-like or Rindle-like, if it's going to be maybe Jarvis over a binary field, you're going to be much better off working in the same ambient field, so working over a binary field. In contrast, if your client asks you to build something for Peterson hashes because he's already, he already has statements that are going to use that, you're much better off building Starks for a Peterson hash, and they will be over prime fields. And then if your client doesn't care and he says, you tell me what is best, there are still extra considerations. Because, for instance, currently WebAssembly doesn't support binary field operations very well. Or to take another analogy, Ethereum doesn't have good gas costs currently for binary field operations, but it has good gas costs for prime field operations. Another nice thing about Starks is that you can choose. You're not forced to one very particular prime field dictated by various number theoretic assumptions. You have more freedom of choice, but it still it's a very complicated question that in different products will probably be deploying different different fields. It's a great question. Yes.
Yeah, I guess that your application in mind is to verify long proofs on chain. So yes, it is possible, and like this is the short answer. And the way that so Eli mentioned before that at the end of the process, the verifier gets several answers to his queries, and every answer is going to come with a Merkle pass. And then the verifier is going to get a bunch of answers with a Merkle pass that is going to check each and every one of them. So you can basically split this work and have the verifier check some of them in every round.
Yes.
Early on, you said that you were basing a lot of assumptions on symmetric cryptography, and you got some post-quantum resistance I saw. Can you dive just a little bit to avoid being too technical what the assumptions are specifically for Starks?
Yeah. So if you are deploying a Stark in a strictly interactive setting, which means you're willing to wait for a few rounds to happen, then the only assumption you need is that there exists a family of collision-resistant hash functions. That's all you need, which is one of the mildest assumptions that any cryptographer will stand behind. Yes, and now if you want to remove the interactivity, you will be using what's known as the Fiat-Shamir heuristic, or assuming that some fixed function is a random oracle. It's something that we all commonly use in our day-to-day use. I mean, most of us, if you're not tossing dice every time you need to build a new password, we're implicitly using this assumption constantly that various functions like SHA-2 or SHA-3 or whatever those are the assumptions. But again, in the strictly interactive setting, which is very plausible and you could actually imagine it working concretely over various blockchains, you don't even need the Fiat-Shamir heuristic. You only need the existence of a collision-resistant family of hash functions. Yes?
May I ask why is it you mentioned before that purely versions can be shorter and more
Great question.
because like it's just some sort of randomness, be it the Merkle hash of my commitment or the hash of swap. What's the difference?
So here's the reason. The short answer is that it is very plausible then to work with a much smaller security parameter. What do I mean? Assume that you have already committed to, you are the prover. You have committed to your proofs. Okay, for you process 10,000 transactions. You say, I want to update the state of the accounts in the system by this diff file. Here is the set of Merkle commits of this interactive process that is now there. Now, the only thing that the network needs to do in order to accept this is to open up and check a few locations, right? Conduct a few tests. And let's simplify things. Each test gives you 1 bit of security. So each time the network comes to you and says, oh, please open up these entries and I'll check something about them, you get 1 bit of security. And the question is now, what will the network practically decide to work with? So you could say the network wants to work with 80 or 120 bits of security, which means, the network will be asking many questions and many answers are being given. But it's very plausible that the network will say something like this. By now, the point is that the probability of error, the probability of you cheating the network is not anymore in your hands, right? Once you committed to those Merkle paths and you get the randomness, your probability of error is dictated only by that randomness. So working with a security parameter of 40 bits or asking you just 40 queries means that you have a 1 in a 1,000 times billion chance of getting lucky. Or phrased differently, if you're going to bribe and pay and try to work the network so that you get the right kind of randomness for getting away with 40 queries, you would need to sort of rerun the system 1,000 times a billion times, which is a huge number that probably the network will say, we're fine with this kind of error, especially if 10,000 transactions only cost, can only cause whatever, $1,000, what's it called? Like the amount of damage would be $1,000 and the amount of money you would need to pay in order to get this reorganization would be much more than that. But in a non-interactive setting, you cannot tolerate 40 bits of security because 40 bits of security means that you can work off-chain to grind randomness until, after 2 to the 40 chances, which isn't such a large time, maybe it's 1 day of computation, you will find the sequence that non-interactively lets you fool the system. So you could very well be working with 40 bits of security in the interactive setting, and you cannot work with that level of security in a non-interactive setting.
Will it be the same if one of the public parameters is random or it's public or?
You could have the set of full commitments being, so you could have just 1 round of interaction. Practically, that would work fine. You have all commitments put in place, and then you wait for the network to ask you 40 queries instead of 120. But I should emphasize, this is yet again a parameter that our customers, the various blockchains, are going to decide. We can advise them, but if a network says we want to work with 80 bits or 120 bits of security, that's perfectly fine. The prover time is going to be the same. The only thing that will grow by a factor 2 or 3 is the communication complexity and verifier time. Now the verifier time anyways is very small. It's going to be like 1 to 2 milliseconds, so it doesn't matter. The question is about the transmission of proofs. Yes?
Are there any downsides of stocks compared to stocks, or are they strictly down?
There's one parameter which is very important. It is the length, communication complexity, the length of the amount of information that is sent by the prover. It is much smaller in Snarks and in Bulletproofs than it is in Starks. So Snarks are roughly 200 bytes for a proof. Bulletproofs, depending on the computation, are between half a kilobyte and let's say 2 kilobytes, okay? And Starks are between 20 kilobytes to 100 kilobytes. So that is the one, but only parameter in which Starks are worse than, it's an important parameter, but it's the only one. Verification time, proving time, and of course the security assumptions are far better in Starks than in Bulletproofs and in Snarks. Okay, so I guess we'll, yeah? Yes.
Regarding the application of the merkle proofing to Ethereum or other blockchains, what is the hope gain from applying this to Ethereum? What kind of improvements can we expect?
So I will present in a second some use cases, and I'll mention specifically where this can help. Yeah.
So now we'll continue. Yeah, Avihu is going to present our product thoughts.
So let's see if the clicker still works. Yeah, so I'm not going to go over all the potential uses, but I will mention, I will focus mainly on scalability. And in scalability, you can think of products in the infrastructure level. Doesn't matter if it's layer 1 or layer 2. I still call it infrastructure because, for example, I see payments as an infrastructure and not as an application. You can also use Stark to, on the application level, to have dApps which are way more scalable, Stark-powered dApps. And as an example, I will show how you can scale DEX better, but you can also apply this to basically any app that requires a lot of gas per transaction. You can apply it the same to CryptoKitties as you can apply it to DEX. Some other well-known application of zero-knowledge proof system is the one of privacy, and this also can be both on layer 1 or layer 2. We can very well implement shielded transaction over a smart contract. There are other uses which are more on the infrastructure level. Those are bootstrapping and sync. The idea here is that if you want your client to be able to sync on the current state of the blockchain, but without re-downloading all the history and running on it, to just receive the current state with a proof that this is the state that fulfills some conditions. It can help both for the easier case of light clients and for full nodes. And we also have uses for Stark-based crypto primitives, such as VDF and signature aggregation. So in 2 words, in VDF, the idea is that you want some function that even that you know the inputs to it, you don't know what's going to be the output. So you can't play with what's the output going to be. The easier part is to find some function that when you run 1 million times gives you that. The harder part is to verify that the output after running this function 1 million times is correct without the need to run this function again. So this is something that you can very well use Starks for. And there are also other primitives such as signature aggregation. We have many more other potential uses. I will not go in them in more detail now. So let's talk just about scalability. And so Stark can provide scalability to blockchain by off-chaining several. I will separate it to three cases. So the first case is the one of complex computation. Let's say that you have a game or any other computation that you never thought that you will be able to run over a blockchain, because to run it in a smart contract will be impossible. You will, if we are taking Ethereum as an example, if you have some very heavy game and you want to perform the computation for this game and it costs more than 8 million gas, then you are in a problem. So this is the first category. And the second one is batching of simple computation. So the idea here is the following. Let's say that you have a game, for example, CryptoKitties, and the cost per transaction is very expensive because you're running some computation, because you're using storage. This is the third category here. So to apply, if you run the transaction as is, then you will pay high cost and you will be able to put 20, maybe 30 transactions in a block. But if you're taking both the computation and the storage off-chain, then and you're using Stark to just verify that the computation and the update of the storage were done correctly, then you can get a much higher scale for your dApp. And it's very much because of the point mentioned here, that verify 10,000 transactions cost less than 3 times more than verify a single transaction. So this is how such a system can work. There are users. If you want to implement scalability by batching on a second layer, so there is a smart contract. Users can deposit or withdraw to or from the smart contract. Once they did it, they can now play in the world of the smart contract. So the way that it works, they are now not sending the transactions directly to the chain. Instead, they are going to send it to some prover aggregation service or prover node. And what this prover node is going to do is going to take the transaction and send to a contract, not, let's say that there are 1,000 transactions, he's not going to send the full data from this 1,000 transactions. He's going to send them the data needed for the, like the metadata, for example, who transfer how much to who. He's going to send the proof that those 1,000 transactions were correct. For example, if it's simple payments, he's going to prove that the signatures were all correct without sending the signatures themselves on chain. And he's going to send a single proof for all this. And what the Ethereum contract is going to do now, instead of running through the 1,000 transactions and verify a signature for each one of them, or update storage for each one of them, is going to verify the proof got from the prover and update maybe a single state represent the state change. For now, it's still all the users. Notice that all the users of the system, they can still see everything that happens because the transactions gives them all the information they need to know, and the proof shows that they can trust this information. So I'll go over specific two use cases. So the first one will be payment transactions. I'm giving all the examples over Ethereum. So the idea here is, let's say that you want to create a payment system that is more scalable than what exists today on Ethereum. So what you want to do is you want to get some saving in several ways. And what we present here is a comparable, simple way, without too many assumptions, that you can get significant saving over the current state of throughput, let's say 10 times more, so at least an order of magnitude. And this implies also that the cost per user will be lower, and both that the throughput of the system will be higher. So how you can achieve that with Starks? What you're going to do is that, or what you don't need to do anymore, you don't need to send on-chain neither the signatures or to verify them. So the part of the signature in all transaction is now covered by the proof. So you get, for 1,000 transactions, you get now much less transmission because you don't have to transmit the signatures, and you also get less computation because you don't need to validate the signatures anymore. The second thing that you will do to save, to get a higher throughput, is that you can take basically the storage off-chain. So to the question of that guy there that asked what we can do with Merkle proofs, so this is actually a very good example because the one way to take the state off-chain is to represent the whole state. Let's say that the state now is the account balances. So you represent the whole state as a Merkle tree, which is leaves is the accounts balances. And what you want to do is when there is a transaction from A to B, you want to update the leaves related to A and related to B with a correct amount, and then you want to prove that you update those two leaves of A and B, leaf A and leaf B. You update them according to the transaction that you saw. So you saw the right signatures of A, you saw the right signature of B, and you update the leaves accordingly. Now, the nice things about this kind of structure is that you prove miracle passes in a tree where the contract only know the root. So you basically moved from storing the whole account balances in storage on chain to store just the root of the tree that represent the account balances. And the proof shows every time that you update, that you send a batch of transaction together with the proof, it shows that this state was updated correctly. And it does gives us 1 order of magnitude improvement on the numbers today. Just this simple method. I'll go over a specific dApp. So a very famous and active dApp those days are DEXs. And a DEX basically, one major reason to use DEX is that users can keep custody of their funds. Now, there are different, people call many different dApps, they call them DEX. There is a range of, starting from, if to quote some known examples, there is the Oasis DEX by Maker, and they're running everything on chain. So orders, cancel of orders, settlements, everything done on chain. And on the other side, there are exchanges, for example, IDEX that does a lot of the things in-house, but still provide the user with settlement on chain and with the ability to keep their custody of their funds. And the good thing in doing some stuff in-house is that you can provide the user low latency trades and still let them keep custody of their funds. Now the problem of one problem of many different DEXs is that the price user pay per trade is mainly the blockchain cost, and it's especially in times where the network is busy, it's pretty high. So you end up paying more per trade for the blockchain than you pay even for IDEX. And this prevents many different kind of users from using DEX, either because they want to trade with lower amount or because they want to perform some arbitrage, for example. So the cost per operation, this is basically the problem. The cost per trade in DEX is still very high. And because the cost is very high, it's also implied that you can have just, 10,000 users per day, 20,000 users per day, but you're limited. Once you reach the sale, there is no more, it's very hard for you to get more trades to your DEX. So what we are presenting here is a very, again, a simple way without too many assumptions to get at least between 1 and 2 orders of magnitude better cost per trade. And this enables the users to enjoy best of all worlds in the sense that now trade costs are almost close to zero to the sense that it's almost a centralized exchange in the experience. So again, it's a very much similar concept to the one that I mentioned before about scalable payments. Just now the signatures are not for the spending, they are the signatures that you need to verify, for example, from the maker or the taker. So before you had to send them on chain and verify them on chain. Now this part can be covered by proof. So again, you send the trades to a prover node. The prover node is going to verify that the maker and taker, is going to prove, that the maker and taker did sign this trade and send a proof for 1,000 trades together. And also another thing that saves pretty a lot is that now you don't have to store all the balances from all the tokens of all the traders on chain. Instead, you can do it in the same way that I described before, and to just prove every time that there is a trade that you update this state correctly. And so this can give 1 to 2 orders of magnitude improvement on the DEX cost. And yeah, so this is an overview of what you've seen today. If there are more questions, we'll be happy to answer them now or after. Yeah.
In that scenario, is the proving node trusted, or?
Yeah, that's a very good question. So, so there is a verifier which is open source. Probably if you implement it in layer 2, so it's implemented as a smart contract on chain. And once you believe that this verify the correct statement, so you don't have to trust the prover at all. In the sense that if the prover is going to try and cheat, the proof will be not valid and the verifier on chain will not let the state to be updated. To this, everybody will see it and the data will be not accepted by clients.
Thank you. In case of payment system and in case of DEX, am I correct in my understanding that users don't have to deposit their funds into verifier contract?
Yeah, that is correct. Not necessarily to verify a contract. You can separate those two, but yeah, there will be a contract that can do Stark verification and a contract that manages the user funds and calls the verifier contract. But yeah.
And how do they withdraw their funds? What kind of data have they present to contract?
So that's also a very good question. So there are 2 ways that users can withdraw their funds. The easy way, and this is not this is not the only way that should be exist, because otherwise you would trust the prover node. But the easy way is that users can always go and say to the prover node, we want our money, please send a proof to the smart contract that we want to get our money. But this is a way that you don't want to go, because as I said before, it doesn't matter if it's payment system or decentralized exchange, you want to let users be able to control their funds completely. So users specifically, they can present the contract with a withdrawal request, and this withdrawal doesn't require a proof because you are not batching anything. Users can follow the state. The prover node is all the time providing in transaction all the data you need. So for example, if there was payment system, so the prover node sends together with the proof all the data that the proofs connect to. And without this data, the proof will not pass. And once users have this data, they can follow their own account in the Merkle tree and ask it to be released when they want to. They don't need to provide a proof, and they only need to follow their Merkle tree, their Merkle path.
And our balances exist in the form of Merkle tree, or they are listed explicitly?
So there are anybody who follows the chain, because all data is on chain, anybody who follows the chain can show or to present the data wherever he wants. But the data itself is not stored in the contract storage. It's stored on chain, so that the transaction data is there. And when you run on the logs of the contract or on the information comes from the transactions, you can rebuild the whole state. But you don't store it in the contract storage. So this is something that doesn't have to be in the fast memory of whoever ran the contract.
Yeah, but the contract has to know your balance to check your request, right?
So the point is, when you want to withdraw, what you're going to give to the contract is your position, like your leaf position, and show that this position is going with the Merkle path all the way to a route that the contract knows.
So I'm providing
Exactly.
If I understood well, you say that you can have like full homomorphic encryption with this technique also, because you say that you can compile a smart contract and then to put into understand.
Could you repeat the question? I'm not sure.
You cannot have like a full homomorphic encryption.
No, this Stark is not fully homomorphic encryption. It's a zero knowledge proof system.
Okay, you can reach something like
Zero knowledge is a different primitive than fully homomorphic encryption. It is because of that it's far more efficient and it's concretely already implemented in various systems. Whereas fully homomorphic encryption, I'm optimistic it will be implemented, like let's say on blockchains sometime, but it's farther behind. So yeah, so in particular Starks, but also Snarks and Bulletproofs and other things, none of them offer fully homomorphic encryption. In general, there's like roughly 3 decades between scientific discoveries and implementations. So it's not surprising that in 85 zero knowledge proofs were invented, and like around 2000, 15, 16, 17, you start seeing them deployed. Fully homomorphic encryption was discovered 2008. So taking the 3 decades, hopefully it will be faster, but we still have, we're only 1 decade after that. So, yeah.
Yeah, the right one first. So I will separate the answer to 2. So there are 2 ways to run, 2 or 3 ways you can use prover nodes. If you have your own dApp, you can start by just having a single prover node run by, for example, whomever running the website of the dApp. And the point here is that you need at least a single prover node to be run, but once you have a single prover node, you can use the service. If for some reason you don't trust this person who runs the prover nodes, or the prover node dies, you can always withdraw your funds from the service, or you can set up your own prover node. The second way that you can use it for some application, it requires a different, more simple storage management, but then you can run actually several provers, and each and every prover to submit even a different part of the data on-chain, and this is also very much possible, just require to store more of the state on-chain. And there is also the possibility, I guess it's more long-term possibility, that prover nodes will be part of the layer 1 system. So if you enforce whoever generate the consensus or whoever generate the block to also run a prover node on it, then you can have multiple prover nodes. There is never a synchronization problem because all the network agrees about what should be proved next. And this also works very nice. Now about the prover node complexity, maybe I'll let Ali.
So I just want to remind you that we just ran a prover node on a browser in a smartphone. So, then it depends it all depends on the complexity of the computation that you want. So 70 Peterson hashes is roughly the size of a single Zcash style transaction. So the analog of that we just executed, in 16 seconds on single thread on a smartphone. As you increase the size of the payload, if you want to batch, let's say 10,000 transactions, then likely you will do it on, on a larger machine with more memory and more cores. And the larger the payload, you will require, more compute and more memory.
More questions? Yeah.
What did you say about implementing Plasma using Starks?
You mean to save some of the assumptions or games there? For example, you're talking about Plasma.
Immaterial Plasma.
Yeah, but what was the question about Plasma? Sorry.
Sounds like almost complete implementation of Plasma you just described, like smart contract
Okay, so I'll give a short answer and we can discuss it more afterwards. And the short answer is that you can use Starks to help Plasma be more simple. For example, you can prove that when state change happened correctly, or that when you want to withdraw, you don't have to play exit games. So you can use Starks to make Plasma more efficient or more simple. This solution here is not exactly like Plasma. In more than one sense, one point is that in Plasma you have sidechain liveness assumptions, and here you get all the data on chain. So you still have all the data on chain here, and you don't need to trust or to hold a second chain for the liveness of the data and the state. Yeah.
I want to add to that in part because of also because of the Ethereum Foundation grant that we agreed to, and we are in constant discussion with the Ethereum Foundation and Ethereum community, and we're not currently deeply involved in Plasma, but we have open channels with core developers, and I know they want to use some of these functionalities in either sharding or Plasma, and we're of course supportive of that. There was here a question.
Yeah, first of all, great presentation. I wonder what's the state, kind of future state of like open source project that might want to use your technology? Because you usually describe a kind of second layer or integrating it somehow.
Okay, so first of all, in terms of open source, there are the two libraries that I mentioned that are open source, MIT licensed. They are academic grade code, which means that I wouldn't use them for more than getting some estimate of of how it works or for part of learning. Though of course, if others are going to develop them and make them more production grade, that would be fabulous. At Starkware, we wrote a new code base from scratch, production grade. Much higher quality. Okay, in terms of what parts and when those parts will be open source, that remains to be decided upon. We have committed to delivering to the Ethereum community as part of the grant open source versions of the things that we were requested, so of repeated hashes and so on. And again, the most I can say is just that timeline is 2 years. As we already presented, we're very, progressing very swiftly with it, and so likely it will be before, it started half a year ago. 2 years, it will be, I can say this, it will likely be before, 18 months from today. But I can't commit to, we can't commit yet to any strict deadlines. But there will be open source code as part of, at least as part of our commitment to the Ethereum Foundation. I would say that this goes back to, so Avihu was just presenting some of our product discussions. We, at Starkware, we're first going to decide what the product is going to be and how do we reach that. And based on that, we're going to, other aspects of open sourcing are going to depend on that decision. I should say that, I didn't mention all of the systems, but I should clarify this. So we're comparing to systems that also have universality, which means that for any computation that you would like, you can get it, not just for a specific thing. And Mimblewimble, to the best of my understanding, is not a universal system. And
I will.
Yeah.
So in Mimblewimble, if I remember correctly, they are using, they need range proofs. Now you can very much do range proofs both with Snarks, Bulletproofs, or Starks. So the range proof is something that very much in use on blockchain today for confidential transactions, and Monero demonstrates something with Bulletproof with it. You can definitely do range proof also with Starks. It will have its advantage and it will have its disadvantage. As Ali mentioned, the proof size is one disadvantage. Verification time can be much better in Stark. And if you want to talk about Wimble later, now you can do it differently with Starks. I will be happy to do it after.
Yeah.
Okay, so in terms of engineering, what kind of help from the community do you think, or how can us, the community, help with tools, development? How do you see this happen in Starks and zero knowledge in general?
That's a great question. So I guess, as someone who's been doing research on proofs and zero knowledge proofs and efficient versions of them for the better part of 15 years, it's first of all just the fact that people are interested and people are learning about it, reading about it, and then going on to look at code bases for that and then improving them is of course a tremendous help by itself. And there will be more and more tool chains and libraries for various projects, and I'm not saying anything you don't know. In particular, so in Starkware, first of all, I definitely encourage any developers who are interested in trying to integrate with our technology or being interested in it to reach out, and we'd be happy to discuss both here today and tomorrow and at DevCon, and of course by other means. There will be, as I said previously, there will be some parts that will definitely be open sourced, and they will hopefully be very high grade and very readable and extendable, and those can be built on. I guess the ultimate goal of having this plug and play tool chain, where basically you take any code written in some high level language and press a button and get super efficient Starks, or for that matter Snarks or Bulletproofs, that likely is going to take a little bit of a while. Just as with, I guess, if you look at general computers, first they were probably built, by hardware, then machine language assembly code. Much later did you get efficient high-level languages. So it's probably going to go through a similar process. First handwritten things, then a little bit of DSLs and things like assembly code, and then more efficient forms. Yes?
So you explained a lot about the performance characteristic of relatively complex functions, these hash functions, compared, they are relatively complex compared to everyday business operations like adding up stock, inventory, etc. So these are also applications, especially in supply chain management, in context of public blockchains, where I see a lot of applicability. Is my assumption correct that these simplistic additions and multiplications would be trivial in terms of runtime compared to executing the hash functions? Or is this, am I getting something wrong?
No, you're getting it perfectly right. But here, one can take the Zcash example, right? So at the end of the day, what really is going on there is checking that the incoming amounts equal the outgoing amounts, right? That's it. But in order to preserve zero knowledge, you don't want to say where the incoming amounts are coming from. And because of that, there is a Merkle tree that holds all of the coin commitments, and you prove in zero knowledge that you know a path there. And for that, you have to prove all of these, in the sapling circuit, which is becoming live next week, it's going to be a whole sequence of Petersons. So when you look at the number of constraints, or the complexity of proving, what fraction of it is devoted to the logic of addition, checking that the sums are okay, the incoming and the outgoing? I'm sure I don't know the exact fraction, it's much less than 10%, maybe it's 1%, right? Because, those are probably going to be a few dozen constraints or field elements, whereas each Peterson is like 1,300 constraints, and you have 30 of them. So the vast majority is because of the cryptographic operations, but in most settings, if you're going to use a proof system, you're going to require some cryptographic layer, right? Your accounting system, like if it's only about adding and subtracting, let's say the inventory, so if you don't need privacy or anything, then why do you need a proof? Right, so the privacy part of it is probably going to cost most of the complexity. And that's already the case in the few applications that we see.
I suggest that if there are more people who want to talk or more questions, that we will take it outside now, and then everybody can have.
I think our session runs till 3:15. No?
Okay.
No, but maybe let's take a 5-minute break so everyone who wants to go out can go, and we'll stay here till 3:15 if you want to continue asking. Okay. So thanks very much.
Thank you.